So recall that last time I was talking about uh, what are injective modules and flat modules. So in this video I will talk about injective modules as well in details. So recall that first. Q is said to be an injective R module if this contravariant functor is exact. And we have seen as an characterization that Q is injective if and only if any short exact sequence of R module starting from Q splits. But now we can do a bit more stronger result than this. So let me just state it as a proposition. So Q is injective if and only if every short exact sequence starting from Q, but this, let me call this C, splits where this C is a cyclic R module, where C is cyclic R module. So it is enough to see whether any short exact sequence that starts from Q and ends at a cyclic R module splits or not. So one part is obvious because if Q is injective, then any such short exact sequence splits. You don't need to require the fact that C is cyclic or not. And for the other part, let's see how we can do. So we'll use the Bayes criteria. So we take a morphism, we take a module homomorphism from an ideal I to let's say Q, and we'll show that it has an extension from R to Q. So let's consider this I to R and this projection. So this is a short exact sequence. And now from I to Q we have, let's call this map as say F. Okay. And now we can take the push out of this diagram that I to R we have inclusion, I to Q we have F. We can take the push out of this diagram. Let's call it say P. Okay. And then now what we have that so so P is a push out of this diagram. That means this square is commutative. And we can complete this diagram by taking this map as the identity map such that both the squares are commutative and the bottom row is also exact. And more importantly, R mod I is generated by 1 or the image of 1 under the canonical projection, right? Generated by 1 bar, let me call this, where this 1 goes to 1 bar. So this is cyclic R module, which means that by assumption, this um, bottom sequence splits. So if we call this beta, we get section beta prime, such that uh, beta prime composed beta is identity on Q, right? And now it is easy because now what we needed to have a map that extends F. So we can define that map F tilde from R to Q as, say, the composition of, first you go from R to P, let's call this map say gamma. Let's first apply gamma, you go to P, and then from P to Q we go to beta prime. And now then it is clear because if you compose it with the inclusion, you get that beta prime compose gamma compose inclusion. But because this square is commutative, gamma compose inclusion is same as say first we apply uh, F and then we apply beta, right? And this is again identity. So identity compose F is F. So you have from Bayes criteria, uh, Q is injective. There is a bit stronger condition. characterization. So this is the first proposition. And so the next proposition is easy. I'm not proving it. It just says that it's saying that any finite direct sum of injective modules is injective, which is you can just apply Bayes criteria. And from definition, you will see. So it says that any finite direct sum, or in this case, both coincide. So you can talk about direct product as well. Product of injective modules is again injective. That is really easy to prove. I'm not doing it. And so now, so here, proposition 2 says that any finite direct sum or direct product of injective modules is injective. Now the question is whether any arbitrary direct sum of injective modules is injective. So the answer for that is in general no, but it's true when you are talking about the ring over which you are talking about the modules uh, is uh, is Noetherian. So in particular, let me just state it first. So it says that R is Noetherian. So first let's assume R is Noetherian. So if R is Noetherian, then any direct sum of injective R modules is again injective. And also the converse is true. That is, suppose you have any direct sum of injective modules is injective, then the base ring is Noetherian. And the converse holds true. So let's see this proof. Not very difficult again. So what do we do? Suppose R is Noetherian and we again apply base criteria. So we start with any ideal I of R and any map say from I to any direct sum of injective modules. So the index set J could be anything. So now what we do is, so now for any X in Qj, or maybe let's see, because we are talking about a direct sum, eventually every element in the direct sum is zero, right? So in particular, if we consider this set that says, let's say all the elements k in J, such that if I write it as X is say Ej or say Xj, you can write it as a sequence. So all the indexes for which Xj is non-zero, let's call it as Sx. So each of these sets is a finite number of elements, right? Because we are talking about a direct sum. And now we need just an extension R to this direct sum of Qj. And also because R is Noetherian, this ideal is finitely generated. So let's just call it this. And so each for each f of say Aj, we can talk about this set S of Faj, and that set is again finite because of this reason. And now then we get, if we take the union of all such uh, S f of Aj over J in J. So now what we can do, take this union, and thus, or maybe I should just maybe it's getting confusing the notation. Let me just call it f of say ai, because we have already used g as an index. So let me just call it ai. So yeah, and this I is running from 1 to n. This set is finite, right? And so what we get, that for each f of ai, all the elements that are non-zero in the coordinate, that collection is finite. And so we can just take uh, so this S is finite. So maybe, yeah. So this is injective, right? Because it's a finite direct sum of injective model. So this is by the last proposition, which I did not prove. So this is injective, and essentially F is mapping I uh, to this collection, because everything apart from this, like everything that F takes outside this is zero, and you can take the inclusion to this, right? So this is our F map, and because this is injective, so we can view F as a map from I to direct sum of Qj over this finite collection, and this has an extension from base criteria. Let's just, yeah, so let's just call this as F tilde, and now it's easy because we have already constructed a map from R to this collection, and we can just take the inclusion to embed it inside the collection that we have started. So we get a map F tilde, and because this first portion is an extension of F and the rest of the things we are just taking the inclusion, F tilde is extension of F. Yeah. So indeed we get that uh, from the base criteria, and so this direct sum of Qj is injective. Yeah. And now what about the converse? So the converse is just suppose given a ring R such that any direct sum of injective R modules is again injective, then the ring must be noetherian. So let's see how to do the converse. So suppose if possible that suppose R is not noetherian. So suppose R is not noetherian. Yeah. So that means you have a strictly increasing chain of ideals. So there exists I1 which is strictly contained in I2 and so on. Yeah. Because it is not noetherian, so you have such a chain. And let's take all the union of ions. Yeah, and each I mod in is then non-zero, right? Because everything is increasing properly. And now I'm going to apply one result that I will prove after this. So let's just assume for now that any non-zero module can be embedded inside an injective R module. So by that proposition, so it's called there are enough injectives in the category of injective modules. So yeah, so maybe I can write this proposition here. I will prove it after this. I should have done it before, but never mind. Uh, so any R module M can be embedded inside an injective module. Injective R module, in fact. Yeah. So any R module means any non-zero R module. So that is all. So for each n, this I mod in gets embedded inside, say, some injective R module. So this is injective R module. And now, so my claim would be that, so by a hypothesis, this direct sum is again injective, right? Because we've assumed that any direct sum of injective modules is injective. So, but my claim is this is not injective. So that will be a contradiction. Yeah. And so how do you do it? So again, we apply Bayes criteria to see whether there exists such a map which does not admit any extension. So for that, the most natural map would be to take, say, let's say we take I and we map it to direct sum of I mod in by just taking x, and at each coordinate you take x modulo in, right? You can take this, and again we can embed it inside this. So we get a map f from I to direct sum of en. And now my claim is this f does not have any extension. So let's see. So firstly, because uh, this module is non-zero, let me just take any for a fixed index. Let me just take am, which is in I minus I. So let this. And so we get that am mod im is indeed non-zero, obviously, because am is not inside im. And now suppose if there exists an extension, so if there exists f tilde from R to direct sum of En such that if tilde compose the inclusion becomes F, then I can take, let's see, F tilde of AM now, but yeah, because it's a module homomorphism, I can write it in this way. And now what is this element? Let me just call it as, say, Bn, right? And so this means this. But this means what? Because AM is non-zero element, so it means that each of Bn is non-zero for all n. But that is problem because because this sequence Bn is a member of the direct sum of En. So eventually it has to be zero always, right? But that is the problem here. So this problem shows that there is no extension, and from base criteria this is not injective, which indeed implies that our earlier assumption was false, and that R has to be uh, R has to be notated. Yeah. So this is this. And now so we have to prove this proposition. So this proposition has two parts. So let's see. So first proposition, uh, yeah. So first I will show that any injective module can be embedded inside an abelian group, or an any module can be embedded inside an injective Z module or an injective abelian group. That is easy because so first step is any R module can be embedded inside an injective abelian group or an injective Z module. Yeah, say Q. That is easy because you start with an injective R module M, you take its generating set, and you can always write M as a quotient of some free module, right? Because you can take the free module generated by the elements of M, you take the surjection and take the K as the kernel, so you get M is isomorphic to F mod K. And now you can embed, because we're talking about over Z module, so this F is a free abelian, and just you can embed it by taking as many copies of Q, I mean as many copies of rational as there are elements of F. You can embed inside this, you can embed this quotient. And remember, over a PID, that is Z, injective module is same as divisible module. So this thing is divisible because direct sum of Q these are, and also the quotient of divisible module is again divisible. So it means that this thing is divisible, means injective. So we get that M is embedded inside, M can be embedded inside an injective Z module. And moreover, this Q, which is an injective Z module, can be given as a R module structure. How? So Q is, let's see how to do it. This part is a bit tricky. So yeah. So now my claim is home this. I can take this module and that. So what we do is first we have that M is isomorphic to home R comma M as R module. That is obviously because if you take an element X and you map it to the multiplication by that element map. So this becomes an R module homomorphism. And now any R module homomorphism is a abelian group homomorphism. So you can write it in this way. And now this by the earlier part inside this because M can so you can identify now M as a submodule of Q because M is embedded. And now my claim is this thing is an injective R module. Let's see how to do it. So not this, yeah. And so for that, first let's give it an R module structure, and the structure is easy because it starts with an element R and an element from home. So you get that RF that should be a map from R to Q. So RF, let's say acting on any R prime. Let's see. So I think this should work. Yeah, I hope this should work. So this gives it as an R module structure. Or maybe, yeah. So I think this should work. Or maybe you can just switch the role of R and R prime. I think this should work. But yeah, you can just check the module definition. I think this should work. And now the main thing, why it is injective? So for injective, what we need? We need just home dash comma home or comma q. So we need this functor to be exact. But by home tensor adjunction, if you remember from one of my last videos, that this is just naturally isomorphic to home dash tensor R comma Q. And so this is just the composition of this functor, right? First you tensor it with R and then take this. And now the second thing is this tensoring with R is naturally isomorphic to identity functor, right? Because any R module, if you take M tensor R, that is just M. So that is naturally isomorphic to the identity functor, which is exact, of course. And by assumption, Q was injective. So this is again exact. So composition of exact functor is exact. So it shows that this is exact, and that indeed implies that hom R comma Q is injective as R module. So yeah, so we prove this proposition, and in fact, for projective modules, that is a lot easier to do because like any R module can be embedded inside a free module, and any free module is projective. So and also any projective module is flat. So it's really easy to do. Like it's really easy to embed any R module inside any projective or a flat module. But it's a little bit tricky. But now we have seen. So yeah, and yeah, so we get that. Yeah, so we have seen that any direct sum or finite direct sum of injective modules is indeed injective. And also just to note, for projective module, if you have two projective modules, P1, P2, and you can take the tensor product, that is again projective. That is just again really easy because this is again by home tensor adjunction property naturally isomorphic to this, which is first you apply the home P2 dash function and then apply P1 dash, but both of them are exact because P1, P2 both are projectives. So this is exact. So yeah, so tensor product of two projective modules is again projective. So yeah, this is just some of the basic things you can do it. So yeah, let me stop this video here.